Okay, so the next set of slides to cover are what is machine learning? Just kind of a high-level overview. Okay, so what do we want to do in machine learning? So here's an example of a few tasks which you can find in many fields: science, engineering, medicine, business, whatever. So first, one task would be prediction. Given some data, you want to predict what's going to happen in the future. This is also known as regression in statistics and in machine learning. So we'll often use the word regression. Another one is classification. So you have some data and you want to classify it. Is it A, B, or C? And then the third one is what you can call categorization or clustering. Somebody gives you a bunch of data and they ask you to organize it. Can you partition this data into different pieces that are similar within and different across pieces? So we'll talk about these just in a little bit more detail now. So first one is, like I said, prediction or regression. So here's an example. Say you want to use current and past data to predict a future stock price. So the traditional old-fashioned approach would be talk to an expert, an economist, ask for a mathematical model of the stock market, and then based on that mathematical model, try to use that model for prediction. So the trouble with that is the stock market and many other processes are very difficult to model. And so there's many, many theories and all that, but if you try to actually make money in the stock market with these theories, they don't really work. So that would be the old way. Machine learning gives us a new way. But overall, the task is to estimate one or more unknown values from a given piece of data. So this data we're talking about could be very heterogeneous. It could be, for example, so this picture is showing stock price versus time. And so maybe I'm trying to predict what's going to happen here. So I could use all these previous prices to predict some future price. But that's not all. Maybe I want to go to Twitter feeds, and I want to somehow use that data as well. Maybe I want to go to other stocks and use them as well. So this idea of data can be very general. From all this data you collect, you want to somehow learn some way of using all of that to predict forward. So that's the goal. Okay, so classification. Here's an example. Say you want to recognize a handwritten digit somewhere between 0 and 9. So here's pictures of what you might be given. So you might be given any of these little blocks. So someone says, "What is that?" Or "What is that?" And an example of this would be you're the post office, you get a letter, rather than having a human read and try to decipher the address, you want to give this to a machine that just scans it and automatically figures out the address from the handwriting on there. So here again, when you ask, okay, how exactly do we do this then? Someone's going to give us a little image about that big, and we have to report one of these 10 digits. So the old-fashioned way would have been come up with some sort of model of what is a 1, what is a 2, what is a 3, what is a 4, and then somehow use that model to make your function that takes this little image and gives you out a digit. But if you think about it, even for this really simple example, and someone says, well, what exactly is a 4? Where's the boundary between 4 and 9, for example? Like this thing, you could say is kind of ambiguous. This could be a 4 or a 9. Or you could, but the boundary between a 7 and a 1, and so on. So it's kind of difficult to actually come up with clear rules and models. So instead of this, with machine learning, what we try to do is we just try to learn from examples. We have many, many pieces of data that are examples of zeros, examples of ones, examples of two, and we try to come up with a general purpose. Could be an algorithm, or it could be some sort of little processing engine, and it learns from seeing all these examples how to come up with a good way of classifying. So more generally, classification is identifying which of k known categories best describes a given piece of data. Okay, this is just one example. There's many, many other examples we'll see throughout the semester. All right. Next task we mentioned is categorization and clustering. Say we're given a collection of text documents and we want to categorize them, but we have no idea of what they should be in advance. So here's our pile of unorganized documents. We somehow need to put them into different categories. So this is an example with text documents, articles or whatever. But this is a very, very general idea. You could apply it to anything, really. So here's another illustration of something similar where you're given pairs of numbers. So you have like x1 and x2. So each one of these pairs is a dot. So this is what you're given, and you're asked, can you cluster, categorize that into we often call them clusters. So as a human, you can look at this and say, oh yeah, it's actually pretty easy. Like this is probably one of them, this is another, and this is another. But that gets at the heart of what clustering is trying to do. In practice, it's not going to be as easy as these little toy examples like this. It's going to be much more complicated, but that's essentially the heart of what we're trying to do with this task. Okay, so these are just 3 of the most well-known tasks in machine learning. There's many other ones as well. We'll talk about some other ones like dimensionality reduction and other ones, but it's just to try to give you a flavor of what we mean when we say machine learning, what kinds of things the course is going to be trying to do. Any questions so far on any of these tasks? All right. So how do we solve these tasks then? Like I mentioned, the traditional approach is to obtain a model from a scientific expert and then apply that model to the task. And there's lots of applications where this is exactly what you want to do. For example, circuit design. Ohm's law works extremely well. There's no reason not to use it. So when we want to design circuits, we don't have to start from scratch and pretend like we know nothing about physics or anything. No, we know the equations, we know how to use them. It makes a lot of sense. But sometimes this traditional approach doesn't work. So one of them we talked about was the stock market. So we don't really have any good scientific models for the stock market. It's not like Ohm's law. So in that case, we have to do something else. So what we're going to do is build a model based on many examples. So you can watch the stock market, over and over and over again, millions of times, and maybe if you watch it enough and you have a powerful enough sort of pattern recognizer, you can figure it out. Another example is sometimes we do have good scientific models, let's say for acoustics, but these models depend on many, many parameters that are unknown when we'd like to use them. So one example of this would be noise cancellation. So in noise cancellation, there's some annoying noise or maybe many annoying noises or echoes or something that are getting involved with our ability to hear what we want to hear. So for example, maybe we're in a lecture hall with terrible acoustics. And what's happening is my voice is hitting all these walls as well as going to you directly. And the echoes are so bad that it's very difficult to hear what I'm saying because of all the echoes. So the equations for acoustics would describe perfectly the situation, exactly how the echoes are going to form and all that. The trouble is that in order to really apply them, you have to have a perfect model of the room as well as all the things within the room to understand how all those equations play out. And those things might actually be changing. Maybe people are moving around, or maybe the source of the interference, maybe it's a siren that's moving around. So there's so many unknowns that you would need to know to even apply the equations that it becomes impractical to apply those equations. So here again, rather than trying to apply the equations, maybe it's better to have something that is learning in real time. And that's essentially what happens with like noise-canceling headphones. They are doing some on-the-fly learning of just what they need to know to cancel the interference, rather than applying some theory based on acoustics. Okay, so that's what machine learning is relative to the traditional approach, where you get some set of equations from a scientific expert and then you use those. So now, how exactly do we do this machine learning? How do we learn from examples? So this is sort of a mathematical viewpoint. And all these little pieces in this mathematical view are things that you will learn over the course of this semester. So first of all, there's going to be a modeling function. We'll write it as f sub theta. And this function also takes in some data here. And it depends on many adjustable parameters theta. So these are the parameters in the model. So for those of you who know a little bit about neural networks, a neural network is a very general processing structure that has possibly millions of little weights that you need to figure out how to tune those weights. So the weights would be theta. That neural network takes in some input. That input goes into this f theta function to produce an output. Okay, so that's this modeling function. So now we need something else to tell us whether the model is working or not working and exactly how well it's working. We're going to call that the loss function, and it often has the variable j. This measures how well the model is performing. Third, we need a training data set on which to evaluate how well this model is working. So typically this training data set is very large, or at least we would like it to be very large. These are all the examples we want to learn from. And finally, the last piece of the puzzle is we need an optimization algorithm that can find those parameters theta that make the loss small on the training data set. So again, you start out with this modeling function. You start out with maybe absolutely no idea what these parameters should be. You start to look at your data, and what you do is you have an algorithm that says, oh, I think if you move your parameters in this direction, the loss goes down, which means you're doing a better job matching the examples that have been presented to you. And you keep changing these thetas little by little, and maybe over thousands of iterations, you finally get to the point where your modeling function is doing a good job predicting the data that you have. And so this is, generally speaking, how things are done in machine learning, how you tackle all those tasks that we described earlier. So here's an example if we want to apply these concepts to stock market prediction. So let's say our goal is to predict a future stock price, which we'll call Y. And Y is just going to be a real number. And let's say that our currently available data is current and past prices of the same stock. So this is just kind of an easy case. So these are the current and past. Each one of those is a real number. if I put those real numbers together and I stack them together into a vector, in this course, I'm always going to use boldface notation for these vectors. So this boldface x, that tells us it's not a scalar value, it's a vector. And if I have d different real valued scalars in it, then this is a vector in d dimensions. Okay, so what we have here is we have predict a future stock price y from the data x. That's the goal. So next we have a modeling function. In this case, the modeling function should input x and output an accurate estimate of y. That's the goal. We would like the modeling function to predict y from x. Simple as that. Like I said before, there's all kinds of different ways to build these functions. We'll learn many throughout the course. One of the ones that works best and getting a lot of attention now are deep neural networks. Okay, how do we know whether a modeling function is working as we want or not? We need a way of quantifying that. That's what we use the loss function for. This loss function j quantifies the accuracy. So in particular, let's call the output of our modeling function y hat. And the hat means it's an estimate of the true y, but it's probably not going to be exactly the true y. It's probably going to be a little different. When I start out, it's going to be very different. I have no idea. The model is not tuned, but maybe if we do better and better tuning our model, y hat will get closer and closer to y. Okay? So we have this quantity y hat, which is our prediction. This is the prediction of the true stock price y. So how do we build the loss? Something like this. You take the difference between y and y hat and you square it. If y and y hat perfectly agree, your loss is 0. That's the smallest you can possibly get when you square something. The more the disagreement between y and y hat, the larger your loss. So your objective is to make your loss as small as possible. The square is not the only option. Another option would be the absolute value between y and y hat. We'll see these different options come up through the semester, and we'll understand a bit more about what might be the advantages and disadvantages of the two options here. Anyway, so now we have, let's think what we have. So we have this, we have our predictor fy, we have our data x and y, we have our loss, a way of telling whether we have a good agreement or not, and finally we need some data to work on. So we have a data set, x, y pairs. So notice that each one of these pairs here is one example of an x and a y. But here I'm going to have many examples. In particular, I'm going to have n different examples. I want many, many examples so I can learn the pattern between x and y. So I want n to be as large as possible. And finally, putting this all together, we need an optimization algorithm that finds the value of theta, the parameters of our model, that minimizes the loss on our training data set. So it all boils down to this equation here. So here's the loss. This loss is looking at comparing the true yi with the predicted yi. This has a little hat on it. Remember that the predicted yi is the output of our model to the input xi. And now this is averaging over all the different i's that we have. So this is the average loss between the true and predicted outputs. And what this is saying is find the parameters theta of the model that minimize this loss and call them theta hat. Once you've done this mathematical optimization and you have those theta hats, you now can plug those into your model F. You have F of theta hat. This is your trained predictor. Now you can plug in your stock market data inside here. Out comes Y hat, and hopefully you get rich. So this is kind of I know this is sort of a lot, put it all here on one page, but as we go through the semester, we will see this to, various granularity, various details. We will learn all these different things. We'll learn different ways of coming up with J, different ways of coming up with F of theta, different ways of doing this optimization, different algorithms to do this. That's what we're going to learn throughout the term. So, like I said, we're going to learn different ways to design this modeling function F, some examples, some buzzwords, linear models, polynomial models, neural networks. We'll learn different ways to design the loss function J. For example, maximum likelihood principle, maximum a posteriori, kernel methods, construct algorithms to do the optimization of the parameters, stochastic gradient descent, our Miho rule, applied to tasks like prediction, regression, classification, categorization, clustering. But that's not all. We'll learn a bunch of other things, a bunch of other important topics, like generalization, which says, basically, even if you do all this to your training data, how do you know that this predictor is still going to work on test data that you've never seen before? That's the notion behind generalization. As a way of improving generalization, we'll learn about regularization. As a way of combining different models, we'll learn about ensembling. And then we'll learn about other really useful techniques for dimensionality reduction, like principal components analysis, non-negative matrix factorization, Gaussian mixture models, expectation maximization, a whole bunch of stuff. So, what do you need? We want to learn concepts and mathematics behind machine learning, but we also want to understand how to implement these things efficiently using standard software tools. So we're going to learn about Python, NumPy, scikit-learn, and PyTorch. Both these things are super important because if you're really good at the software but you have no idea what you're doing, you're not going to be very successful, right? At the same time, if you know all the theory but you can't put it into code and actually do something with it, you're not going to be very successful either. You really need both of these pieces here. So that's why this is a 4-credit course. That's why we have a lab and a homework due every week. It's going to be more work than your typical 3-credit course, but students who stick with it seem to really like it, so they learn a lot. Okay, so what are the prerequisites again? Undergraduate level linear algebra, undergraduate level statistics, and scientific coding. The linear algebra part is super important. It's going to come up over and over and over again. And the trouble is, a lot of the notes and concepts are going to be presented in terms of vectors and matrices. And if, when you look at these vector matrix expressions, they look like unintelligible to you, then you can't understand the machine learning behind them, right? So this is super important. And sometimes I have students tell me several weeks into the course, I have no idea what's going on because I don't understand the linear algebra that you're using to explain the concepts. So for this reason, I added a homework number 0, which is really even before we start into the material for this course, on linear algebra, which is a prereq. So this homework, you can already find it assigned there on Carmen. It's due this Friday. I won't be doing any lecturing on linear algebra per se. I'll cover things as we go throughout the course. But for now, it's on you to just remember, maybe it was several years ago when you took this course. Maybe it was during the pandemic and you feel like you didn't learn it well. Well, now you have another chance. There's a really nice set of notes, a concise summary of just the linear algebra we need that is posted on the main course repository. And if you look through that and make sure you understand the different things in there, and then test your knowledge on that first homework, you should be good. There's also going to be a short Carmen quiz that's due on Friday, which is, again, once you do the homework, that will be the final test to see if you really understand the concepts. Just 5 multiple choice questions, but under a time limit, so you need to be able to do them, relatively quickly. And by paying attention to this and putting effort into this, I think it will make the whole course a lot easier to digest. So I do ask that you take this seriously. And I may even keep putting linear algebra questions on the quizzes throughout the term just because it's so important to understanding the fundamentals of this course. So that's it for these intro slides. Any questions on anything so far regarding material or prerequisites or anything? Yes?
I'm sorry, I missed the first couple of minutes. So you're recording, will these recordings be available regardless? Or?
Yeah, I'm recording these and I'm going to put them on YouTube, and then you'll be able to find them there. I will post the link, let you know. This is my first time doing this on YouTube. I previously did it on Zoom, but the problem with Zoom is that the lectures disappear after 3 months. So I'm trying to see if I can do it more permanently this time. But yeah, it's my first time, so I just made a YouTube channel, and hopefully everything goes smoothly. All right, any other questions? Anything? All right, well, if not, then we'll see you guys on Wednesday, and we'll start into the very first unit, regression.